By the time you're seeing this video, it'll be almost 2 years since I first announced that I had started decompiling LEGO Island, and to be honest, I had no idea where it was going to go. There's a reason I used the word started in the title instead of just saying I'm decompiling LEGO Island, because I really didn't want to make any promises that it was ever actually going to be finished. Yet on December 23rd, 2024, literally just in time for Christmas, LEGO Island hit 100% decompiled, meaning we effectively have the whole game in compilable and editable C++. There's still more work as far as improving the accuracy, the portability, and our overall understanding of everything in it, but the whole game is here. You can compile LEGO Island on your PC from scratch and play through it as if it just rolled off the Mindscape assembly line. In just a year and a half, this was one of the fastest decomps I'm aware of. And while I'd love to pretend that this was all because of me, in reality, there's no way we would be talking about this right now if it weren't for the immensely dedicated team that came together around this project. Even while I was off making documentaries, short films, and Wii U gamepad clones, the team was keeping the whole thing moving, and they are really the reason it got done as quickly as it did. So before we even begin, I want to give a huge shout out and thank you to anyone who contributed and helped nudge this project along. But without further ado, let's get into it. How did we decompile the entirety of LEGO Island? Well, if you've seen the first part of the series, you already kind of know how we did it because I explained the process of decompilation in that video, but just to refresh you, the word decompilation is a bit of a misnomer. It sounds simple, like you're just undoing the compilation process, but no. Decompilation is more like recreating the code from scratch until it produces something as close as possible to the original game. Once again, the cake metaphor is actually pretty fitting. You can't just decompile something in the same way you can't just unbake a cake. But if you spend a long time analyzing the cake and trying a lot of different things, you'll almost certainly eventually produce a recipe that's extremely close, if not identical, to the original. That's, in essence, what decompilation is. It's a very long and laborious process. It's one of those things that's a lot more time-consuming than difficult. Once you've got the process down, it doesn't really change all that much, but you'll be doing it over and over and over for the better part of a year, if not more. It's kind of like going to the gym or learning a foreign language. If you go in thinking you'll be buff or fluent in a few days or even a few weeks, you'll be disappointed. But if you just do a little bit every single day, you'll look back after 6 months or so and be amazed at how far you've come. But that's the kind of mentality and work ethic you have to have. It's a marathon, not a sprint. It's not for the faint of heart. This is where having a small team helps a lot too. These are hobby projects, and sometimes you'll have free time for them and sometimes you won't. But as long as someone is around to keep pushing it along, then you'll all reach the finish line eventually. So if I have any advice for people trying to start a new decompilation project, it's understand that this is likely a several year-long commitment, and also try to find a team that's just as passionate about it as you are. So once you got those, now what? Well, as I've said in previous episodes, you'll definitely want to use something like Ghidra or IDA to help you along. Programs that are specifically designed to assist in picking apart executables. Most of us use Ghidra since it's free and open source. Once again, neither of these tools can produce a working decompilation of a program, but what they do provide is a lot of tools that help you better understand it. For example, when you're looking at a particular function, they can provide a pseudocode representation. Not real code, but something that's a lot more human-friendly. It's not perfect by any means, but it is usually pretty accurate. You may occasionally need to reference the assembly to really understand what's going on, but for simpler functions, it's often enough to just paste this into your code and clean it up until it's actually compilable. As you learn information about the game, you can provide information back to Ghidra or IDA, and its results will steadily improve, helping you even more. You'll start to see things you discovered earlier pop up in other places, helping you understand those too. Like if you figure out the type of a variable, it'll propagate to everywhere else it gets used. This cycle continues basically until the end of the project. Ghidra giving you information, you giving it information, it giving you more, until hopefully, eventually, you both have a pretty complete understanding of it. But something we found with the LEGO Island decomp was that it was actually pretty cumbersome to feed that data back into Ghidra. Like after hours of work, we'd finally solve a particular struct or function just to get extra homework putting all that information back into Ghidra. Most of us simply never did it, meaning the Ghidra repository quickly fell behind the decomp itself, becoming less useful than it should have been. So eventually, team member John Shiz wrote a Ghidra script that automatically populated it with data from the decomp. This made it easy to keep the Ghidra repository up to date so we could really maximize its usefulness. Funnily enough, all this information started causing my Ghidra server to run out of memory. I had to change its configuration just to keep it from crashing every couple of days. But in a way, that's a good thing. We're really getting as much as we can out of our setup. Okay, so that's the refresher. That's broadly what's happening whenever you're decompiling something. But how do we know we're on the right track and decompiling good? Well, that brings us to the topic of matching. Early on, we all discussed what level of accuracy we were going for with this decomp. There are basically 3 options. Byte matching is for those who are real perfectionists. Basically, your goal is that your decomp will compile to exactly, byte for byte, the same executable. This is obviously the hardest and most labor-intensive option, but there's no debate that your code is just as good as the original source code. I mean, the results confirm it. Instruction matching is a step below. A program's code is basically just a collection of functions, and rather than trying to produce exactly the same end file, the goal here is that each function compiles to the same machine code. In general, this is a lot more practical than a byte match, since you're just trying to make your code do the same thing rather than recreating every single eccentricity that contributed to the final executable. And the result should still play exactly the same, since the code is obviously the important part. Finally, there's non-matching, though you can also call it a functional match. This is where you don't explicitly try to make the code identical, you may not even write it in the same language. You just try to make sure each function produces the same results. You'll still look at the original code to see exactly what each function does, but if the resulting instructions from your decomp aren't in quite the right order or aren't using exactly the same registers, it's not a big deal as long as the end results are the same. None of these approaches are wrong. Done right, they'll all achieve what we want out of a decomp, a modifiable codebase that compiles to one of our favorite games. It's just a matter of how perfect you want it to be versus how much effort do you want to pour in. If you remember, I had first tried to decompile Lego Island back in 2019, and since I'm a perfectionist, even back then I was aiming for a byte match, just for the satisfaction of knowing this was as close to the original source code as we could possibly get. But this time, I was a little more wary. I mean, I'd already bitten off more than I could chew before, so I was once again hesitant to commit to anything big. The team that joined after my first video were also interested in aiming for accuracy, but they also knew, as much as I did, that this would be an uphill battle, so we ultimately decided on a bit of a compromise. Helpfully, these approaches aren't mutually exclusive. You can always start with something rough and make it more accurate later on. So our goal was to aim for instruction matching whenever possible, and then see if we could work our way up to byte matching later on. This wasn't just for the satisfaction of getting close to the original, there are practical reasons why instruction matching tends to be good practice. Sure, you can decompile without it, but how do you know you got a function right? I mean, you can stare at them side by side and be pretty sure you have, but what if you made a mistake, or missed something, or thought something wasn't important when it was? Realistically, you can't be 100% sure unless it actually does exactly the same thing down to the instruction. Matching the instructions is more work, but it also gives us the peace of mind that our code is faithfully recreating the game. To help us with this, I wrote a Python script called reccomp. Basically, it does what a lot of existing decomp tools do, which is provide a diff between the original code and the recompiled code. However, my tool has a slight twist that really helped us out. Firstly, we would have had to write some tooling anyway because most decomp tools, at least at the time, specifically target old console games, not Windows 95 games. We could have just forked something, but I wanted to go a little further with it. Above each decompiled function, I put a little annotation that specified where in the original file it came from. Then, as long as we compiled with debug symbols enabled, it could use those to see where that function was in our version. From there, as long as we kept those annotations on every function, this script could tell us anything about any function in the project. We could use it to get immediate feedback on how accurate a function was while we were working on it, but also, since it had complete knowledge of the entire project, we could use it to track the whole thing. How much of an impact a particular contribution had made, if something had caused a regression. Reccomp became our main feedback loop and way of measuring progress. This is another thing I would really recommend if you're starting a new decompilation. It doesn't have to be reccomp, but find or create plenty of tooling, because for such a big project, you're going to need as much help as you can get. Over time, team member Disinvite expanded reccomp even further to check things like virtual tables, the stack layout, global data, struct sizes, because this compiler is too old for static assert, and more. These too provided a major boost to the decomp and our ability to track progress and accuracy. Everything would have been perfect if it hadn't been for... Decompiling a game can be as much a study of the game as it is the compiler that the developers used for it. Sure, it matters what source code went in, but ultimately the compiler is what generated the stuff that you're looking at, so to get back to the source code, you're going to need to have an idea of how it did it. When it comes to instruction or byte matching, you really need to find exactly the same compiler that was used in the original, and I mean exactly. There are so many variables when it comes to what assembly is generated. Compiler developers are constantly changing things, trying to get more optimal results out of the CPU, that realistically your only chance of even getting close to the same binary is starting with the exact same compiler with exactly the same flags, both of which you're probably going to have to figure out yourself. Thankfully, compiler identification isn't usually too hard. They usually leave some kind of metadata about themselves in the finished program. For LEGO Island, Mindscape used Microsoft Visual C++ 4.2 from 1996, and thankfully they appear to have kept all of the compile flags stock. Unfortunately, even with the same compiler, the same flags, and accurate decompiled code, you still may not get identical assembly. Why? Well, like any language, there are a lot of different ways to accomplish the same thing in x86 assembly. None of them necessarily wrong, but different. So how does a compiler decide which one to use? Well, in the case of MSVC, the short answer seems to be it doesn't. It instead leaves it up to, apparently, RNG. Okay, not literal RNG, it doesn't change every compile. What happens is, for any given function in a file, if you make any change to that file, including changes that don't affect the function at all, and including changes in any header that's included in that file, MSVC may pick a different way of compiling that function. We've called this phenomenon compiler entropy. It's like it's random, but it uses the file itself as the random seed. Or something? We've never really known exactly what causes this. We've found a few ways of influencing the entropy, like adding empty variables or meaningless extra lines or whatever, but nothing consistent. The result is functions will randomly fluctuate as we keep adding code to the decomp. Code that was an identical match before will randomly drop in accuracy just to go back up again later on, even when nothing we've done should have any impact on that code whatsoever. In practice, while we had this whole system of detecting regressions, it became impossible to determine whether a drop in accuracy was actually a regression or just MSVC shenanigans. If a function we're decompiling is being exceptionally stubborn, we have no idea if that's because we just haven't nailed it yet, or MSVC is just choosing an alternate way to compile otherwise correct code. This is the entire reason our accuracy still isn't 100% to this day. We can be reasonably sure every function is correct, and most of the functions that don't match today probably did at some point, but with every change, some go up and some go down. It's like an endless game of whack-a-mole. We're still hoping for that byte-accurate decomp one day, but considering how much code is in here, chances are pretty damn slim that one day they'll magically lock in at 100%. The team is currently attempting various brute-forcing techniques to try to get the accuracy up higher, but who knows whether this will get us there either. Personally, I suspect we won't reach 100 without knowing exactly what causes the entropy in the first place, and we'll probably never know that without significant reverse engineering of the compiler itself. I can only imagine what the Microsoft developers were thinking. Like, should we use the test instruction in this scenario or the comp instruction? Should we use the ESI register for this or the EDI register? They spent a few weeks scribbling all over the whiteboard, weighing the pros and cons, and heavily debating it before eventually deciding, fuck it, let's just make it choose at random. I mean, that's my guess, but hey, if you worked on the Microsoft compiler between 1993 and 1996, feel free to shoot me an email and tell me what the hell you were thinking. So despite instruction matching the whole way, our decompilation is still only hovering around 98% accuracy and probably will for the foreseeable future. And honestly, it's not that big of a deal. While we'll probably always hope we can hit 100% one day, it's not like we can't do all the things we wanted to do already. It's merely unsatisfying to be so close, yet so far. There's another thing that complicates our ability to achieve byte accuracy, and that's LEGO Island's usage of third-party static libraries. That's code that other people have written and probably sold as a product to Mindscape that has then been incorporated into the main game. Most of LEGO Island was developed in-house, but it does use a few external libraries for things like decoding smacker and flick videos, and it also uses a custom memory allocator called SmartHeap. Functionality-wise, all of these are pretty easy to replace. With modern PCs, we can get away with the standard memory allocator, and there are plenty of open-source libraries for decoding smacker and flick. But as far as a byte-accurate match goes, you're gonna need to find all of these, and the exact same versions of them too. I mean, you could decompile them too, but since they were real products, it's almost certainly easier to just find them. But that's still kind of hard because all of this stuff predates deployment of software over the internet. Like, these never had download links available. Back then, you would have had to purchase a CD or floppy disk. By scouring through various software archives, I managed to track down versions of SmartHeap and Smacker that were really close enough that they were compatible with the rest of the decomp, but not exactly the right version, so not byte accurate. The Flick library eventually was just decompiled since it was relatively simple, but for the rest, we're still searching. There are more hacky ways that we could extract this library code from LEGO Island and convert it into an object that could be relinked into our decomp. This is useful for byte accuracy, but arguably isn't really in the spirit of decompilation. Like, yeah, of course you can repackage machine code, but aren't we trying to get a modifiable codebase here? Plus, it's not like we'll be able to use most of these libraries for anything other than achieving byte accuracy. I mean, these are obsolete libraries for Windows 95. We'll need to replace them anyway to port to anything else. So, does it really matter? No, not really. Like I said, none of these are particularly hard to replace with open source equivalents. Once again, it's just for the satisfaction of getting that byte-accurate decomp. Okay, so let's get into the fun stuff. One of the biggest advantages to decompiling is the opportunity to port it to other stuff later on. It's been a long-term joke on the channel that one day I'll somehow facilitate a port of Lego Island to the Wii, and well, if I'm going to do that, we're going to have to find a way to decouple this from its Windows roots. Funnily enough, we do know that in the beginning the game was originally planned to be on Macintosh too. A developer even told me that there were early intentions to get it to run on DOS, and you can see early on that they did put effort in towards making it cross-platform. There was this thing they wrote called Thin Graphics Layer, which would have helped to abstract from the various platforms they wanted the game to run on. But at some point, those plans clearly went out the window and they just started calling DirectX functions directly. This is the real problem. The game does make some Windows system calls, but it's fairly basic stuff like creating the window and receiving mouse and keyboard events, things that wouldn't really take too long to rewrite for another platform. DirectX, however, is involved in almost everything. All of the models, all of the images, all of the textures, all of the sound, and all of the controller input. And all of that stuff is only on Windows. Yes, I know you're saying, isn't DirectX on the Xbox too? And the answer is yes, but not this version. Lego Island was written for DirectX 5, which is very different from any version that shipped on an Xbox. So basically, there's no way around it. Getting Lego Island onto something else will require pretty significant modifications to port it away from DirectX. In the short term, we can use translation layers. Early PC ports of Super Mario 64 utilized code from emulator plugins to translate the N64 graphics calls to PC. And even today, most ports use some kind of translation layer so they don't have to rewrite the game's graphics code wholesale. The most mature translation layer for DirectX is a little program called Wine. Wine indeed translates DirectX calls to OpenGL, and it handles Windows system calls too. With some effort, you could rip code out of Wine and stitch it into the game to make it quote-unquote native OpenGL. I mean, as native as those ports of Mario 64 are, but this obviously won't help platforms that don't support OpenGL, such as pretty much every console in existence. Whoops. And as I alluded earlier, we're all perfectionists, so work has already started towards rewriting vast swaths of the game to use cross-platform libraries like SDL. And at the very least, even if SDL isn't available on certain platforms, it's probably still easier to port that stuff than 30-year-old DirectX APIs. But this is still an ongoing process that's really just started. And to be honest, one of the hardest parts is still yet to come. You may see the DRM in this name and think it stands for Digital Rights Management. Thankfully, it doesn't. It is true that the Italian version of Lego Island comes with Securom, but most versions didn't, so we don't have to worry about that. In the early days of 3D, there was a lot of debate about the best ways to do it, and one of those debates was retained mode versus immediate mode. These are convoluted words, but basically it boils down to who owns and maintains the actual 3D objects, you or DirectX. In immediate mode, it's all up to you. You handle everything, and the graphics library is really just there to abstract from the underlying hardware. Retained mode behaves a little more like a game engine. You give it model and texture data, but the library is what actually builds and renders the scene. Retained mode was therefore significantly easier to use, but also provided a lot less control. If something was running slowly, you may not necessarily be able to tell why, and retained mode could bloat your game with a lot of functionality that you don't actually need. Ultimately, nearly all developers preferred to use immediate mode, and retained mode was only seen in a handful of major commercial releases, like Lego Island. But demand was otherwise so low that Microsoft deprecated it shortly afterwards. It didn't make it into the Xbox, and it didn't even make it into Windows Vista. If you've ever opened Lego Island and seen this message, that's why, they just removed it. Ironically, Microsoft does still support all of the other DirectX infrastructure from that era, so you can just restore the retained mode DLL and it'll work fine since it just sits on top of the immediate mode stuff that they still support. Yeah, it's not that D3DRM was too old or anything, it was just so underutilized that they concluded they could just stop shipping it and most people wouldn't notice. Funnily enough, the situation is pretty similar on Wine. They have a D3DRM implementation, but it's very incomplete and can't do much that's useful. But the rest of the infrastructure is pretty much done, so if you restore the original DLL, you can play Lego Island mostly fine. D3DRM has been the elephant in the room for most of the decompilation. Even as we approached the finish line, we still knew that a big chunk of the game's graphics were not handled by the game, they were handled by this behemoth of a library. Lego Island is very much written in the D3DRM ecosystem. porting away from it is difficult because the only thing that really behaves like it is a full-blown game engine, which would likely bring its own baggage with it. We could roll our own custom equivalent library where we only have to implement the subset of features that LEGO Island uses, and we could also always decompile D3DRM as well. Then, of course, we have everything we need and can more easily port that to other platforms. But of course, this is also the most labor-intensive thing to do. After decompiling a whole game, I'm not sure any of us are chomping at the bit to decompile some obscure and obsolete DirectX infrastructure. On the naughtier end, a substantial amount of Windows code has leaked over the years, including the complete source code for D3DRM. I don't think any of us love the idea of using leaked Microsoft code. I mean, decomps are already in a legal grey area, but LEGO doesn't seem to care, and Microsoft might. At this point, there isn't really a consensus as to what the best approach is. All of them seem terrible in their own ways, and it's really just a matter of deciding what the lesser of all these evils are. One of the interesting things about interviewing a lot of different developers for the documentary is that some of them still have stuff that they backed up from the time. About 6 months into the decompilation, one of the developers said that they might be able to help me find the real source code to the game, as in the final retail code, but only if we could get official permission from Mindscape. I brought this up with the admin team, and there were some very mixed feelings. Like, obviously, having the real source code, especially if we could somehow officially sanction it, would be the best possible thing to work from and would save us months, if not years of time. But also, we were on a roll. We'd found this incredible team that had banded together and was making contributions every single day to make this a reality. It felt like such a shame for that to all just disappear. But it would also be unfair to make them commit so much of their time and energy to a project that may not have a good reason to exist. So I decided to look into it. Who owns the copyrights to LEGO Island's source code? The answer is actually pretty complicated, and full disclosure, I'm not a copyright lawyer or anything. This is just speculation based on what I've been able to find publicly. The obvious answer is LEGO. I mean, they clearly own the brand, the characters, and the ability to make more games in the series. But whether they own the copyrights to the game's code is another story. LEGO Island used a lot of Mindscape proprietary code, including components that were used both before and after it. So at the very least, Mindscape must have retained ownership over that stuff. But it would have been fairly complex to tease apart which parts of LEGO Island's source code should belong to LEGO and which parts should belong to Mindscape, especially since the more game-specific stuff would have been pretty useless without the underlying Mindscape engine. Add into this that there probably wasn't much motivation for LEGO to acquire the code. I mean, the idea that you might want to re-release the game 30 years later wouldn't have even been on most people's radar at the time, especially for a company that was brand new to video games. It would have been a fairly standard arrangement for LEGO to have contracted Mindscape to make the game for them, but let Mindscape retain whatever trade secrets they used to make it, and I highly suspect that's what happened here. So if Mindscape retained the code copyrights, who would have them now? Shortly after the release of LEGO Island, Mindscape was sold to The Learning Company, who also purchased Broderbund shortly afterwards. The following year, The Learning Company was purchased by Mattel Interactive in what has been called one of the worst business deals of all time. Mattel, quickly realizing what a mistake they had made, sold their entire interactive division to the Gauze Technology Group. Gauze split up the assets again, selling the entertainment stuff such as Broderbund's Myst and Prince of Persia to Ubisoft, and most of the other stuff to Riverdeep Interactive, now known as Houghton Mifflin Harcourt. Meanwhile, a former executive of the Learning Company purchased many of their international assets and the Mindscape trademark from Gauze. He started a new company called Mindscape in Paris. Apart from the name, Mindscape in Paris really had nothing to do with the Mindscape we know, and mostly what they published was shovelware for the Wii, though we don't know exactly what assets they acquired from Gauze. After going bankrupt in 2011, their assets were most likely sold off to shareholders, though some offshoots in the Netherlands and Australia continue to operate, but only as glorified storefronts. One of these companies most likely is the true copyright owner of LEGO Island's source code, but even they might not be aware of it since they acquired so many assets in bulk. If I was to make a guess, I think it's most likely Houghton Mifflin Harcourt, which also came to acquire Broderbund's Carmen Sandiego franchise. Though apparently they recently sold their media division to HarperCollins, so maybe they own it now. I tried chasing a few of these leads, but didn't really get anywhere. Ubisoft, I highly doubt would ever entertain this conversation, and even though I knew they were several steps removed from the Mindscape we knew, I tried calling the two offshoots to no avail. The Australian one simply didn't pick up.
Thank you for calling Mindscape. The next available operator will take your call shortly.
And when I asked the Dutch one about LEGO Island, they responded like I just asked about 2 girls, 1 cup. Around this time, the decomp made a major breakthrough. After months of nothing but a blank window, the team had finally gotten something to appear.
You have to put the CD.
Okay, so it's a little glitchy, but just to have something appear was a huge milestone, and the culmination of a flurry of activity to implement a substantial amount of the game's disk streaming, smacker video decoding, sound, and display systems, because all of that had to work just to show something on the screen. We call this period the advent of Isle, because it really cemented this decomp as something that had a real chance of working out. And seeing how the team was making much better progress than any of my inquiries with these companies, I quietly decided to drop my search and let the decomp continue. Over the next year, things proceeded at the glacial pace that decomps do, but every now and then we'd hit a huge milestone that reminded us of how exciting this was. The opening logos and dialogue, bitmaps and some cursed facial animation, the observation deck, the hospital, the first 3D objects to render, the first time the whole island rendered, the first character animations, the first time the lighting actually worked, the credits, the first NPCs, the first time the pizza missions and the races and the build sections worked, the first time the game campaign was winnable. And eventually, the biggest milestone, the point where everything was done. Every time we hit a big milestone, I felt inclined to make another video, but in the time it took to write, record, and edit one, another big milestone happened, then another, and then another. It got to a point eventually where I was just like, may as well wait until the decomp is done. I mean, that's obviously what brought us here. Something we were able to retrieve was the first beta to LEGO Island. Now, there was a beta that had been discovered before, actually the last beta before the final release, but it was so close to the retail game that it didn't really give us anything new, except for a changelog that was mildly interesting from a historical standpoint. Beta 1 was different though. It was only a month or two earlier and still largely played like the final game, but there were some critical differences that proved very helpful for the decomp. Namely, unlike the other beta, it had a debug build on it. Not a debug build with symbols, it wasn't that exciting, but it still had a lot of information that was stripped out of the final release builds. For one, the code was unoptimized. Now, if you know anything about programming in C or C++, you'll know that compiler optimizations, as helpful as they are for performance, are a nightmare for debugging code, and likewise with reverse engineering it. You may remember years ago I talked about how the initial release of Mario 64 was unoptimized, and that almost certainly helped that decompilation succeed. Optimizations mean the compiler has kind of rewritten your code to take as much advantage of the CPU as it can. As such, a lot of things will only vaguely resemble the original C++ source code, which is part of what makes decompilation as complicated as it is. But with unoptimized code, the compiler has made few, if any, code modifications. It's a much more direct translation of the source code that went in. No unrolled loops or inline functions, just whatever the C++ did, but in x86 assembly form. We'd still compare our decomp with the retail build since that's what we were trying to remake, but the beta gave us a much better picture of what each function was doing, and was so close to the retail release that most of the information from one would directly translate over to the other. Unfortunately, even the unoptimized code was still susceptible to compiler entropy, so it wasn't a magic bullet. But even so, just having the unoptimized code as a starting point probably saved us months of development time. Additionally, the debug build still had assertions. Assertions are a common debugging tool in C and C++ where if you know a certain condition should never be the case, you can have the program immediately abort if it does happen, so it's then easy to investigate in a debugger. Release builds usually strip them out because, well, even if something does go wrong in a way you don't expect, you don't necessarily want the program outright crashing itself as a result. Assertions commonly have a string that identifies exactly what went wrong and where, and from just seeing these strings in the code, we'd learn the function name, which would often tell us what that code was supposed to do, the class that it was a part of, as well as what was or wasn't supposed to be happening at that specific point in the code. It was the closest thing we could get to original developer comments or documentation, and it too proved invaluable. One of the strangest and most frequently discussed glitches in LEGO Island is the exit crash. For reasons that have never been clear, trying to just exit the game results in everything rapidly losing stability, with its animations and sound glitching, and often the game straight up crashing. I mean, I guess it gets the job done, but you also usually lose all of your unsaved progress in the process. This bug is also the cause of the infamous "Are you ready to leave" glitch.
Are you ready to leave? Are you ready to leave? Are you ready to leave?
It happens so frequently nowadays that it's actually rarer for it not to happen. But here's the thing. It doesn't exist on old versions of Windows. There, exiting works exactly as intended, without even a hint of the bugginess you find on Windows Vista and onwards. What Windows change caused such a stark difference in behavior? Even stranger, earlier versions of the game, like that 1.0 beta, used a different front end written in MFC. And the exit glitch wasn't present with that either, even on the latest version of Windows 11. So it both was and wasn't caused by updates to Windows? What the hell is going on here? One of my biggest hopes for this decompilation is that it would reveal the true cause of this exit glitch. I had been partially able to fix it with patches, but only to stop the game crashing and losing your progress. The animation and audio glitches I never found the solution to. Well, I'm incredibly pleased to finally reveal the cause and solution of this bug. There are still some questions about it that we don't have the answers to, but this is what we found during the decomp process. This is a function called windproc. It's a standard function you write when making a Win32 app. It's basically the event handler called whenever Windows needs to send a message to your app. Windproc is in the front end. Remember, the retail front end was completely rewritten from the one in the beta that doesn't exhibit this issue. Both windprocs relay important information back to the main game, things like mouse movements or certain key presses. But do you notice something kind of odd about the retail windproc? Anything that could potentially be problematic? If you said, this variable may not always get initialized, you're right. In some cases, it may not, and there's no check to ensure it has been set before it's sent over to the backend. In C and C++, if you don't assign a value to a variable, then the value in it will be effectively random. Well, it'll be whatever was in that memory before, which could be anything depending on what else is running on your system. So in some circumstances, the front end just ends up sending a bunch of random events to the backend, which wreaks havoc on the exit animation. The fact that it happens in the windproc also explains why moving the mouse can make the glitch significantly worse. The beta front end, pre-rewrite, is written in a way that never sends an uninitialized event type to the backend, so it's never an issue there. I'm not sure what necessitated rewriting the front end at the tail end of development, but it's hardly surprising this ended up introducing bugs. If we rework the code in a way that it'll never send a random event to the backend, the issue magically disappears. But we don't exactly know yet why the exit animation is specifically affected, or why it mostly happens on later versions of Windows. Paradoxically, even though we've decompiled the whole game, that doesn't mean we have a complete understanding of the whole game. Matching instructions doesn't require us to know the purpose or context of a piece of code, just that it does certain things that we try to recreate in C++, and hopefully it'll all fit together at the end. There's still a lot we don't know and are figuring out as we go, and this is definitely one of those things. But at least we more or less know the main culprit and how to fix it now. While there are a lot of people who showed up to contribute to the LEGO Island decomp, if there was one person most responsible for bringing this project over the finish line, it was foxtacles. Unlike my measly 5 or so years of wanting a decomp of this game, foxtacles had first thought about it 15 years ago in 2009. He emerged early on as a major contributor to the project, and he eventually rose up to join the admin team too. Unlike myself, who prefers to bounce around a number of different projects, foxtacles thrived at focusing on one long term, which is a fantastic trait to have for a project like this. He was really instrumental in managing the team and diligently keeping everything rolling the whole time. If it weren't for that, I think there's a good chance this would have stalled a long time ago. To be honest, as much as I hate to admit it, I was kind of the DJ Khaled of this project. I wasn't the most talented. At the end of the day, I didn't even contribute the most. My biggest contribution was managing to bring together the right people who could pull this off. And pull it off, they did. Now that we can compile the entire game from scratch, I thought it would be interesting to build on both a modern PC and a PC from the era, just to compare. As a programmer, it's kind of fascinating to have the complete source code to a game you played as a kid. Like, this is it. This is all the code behind all those nostalgic experiences I had. Back then, LEGO Island felt pretty big, but today it's undeniably an old and primitive codebase compared to anything we're compiling today, so make your bets. How fast do you think these will finish? Let's start out with a Pentium 120 running Windows 95. This is my best guess for the kind of hardware the developers would have actually been making LEGO Island with, since it came out in March 1995, just before development started, and is listed as the minimum system requirement for actually playing the game. Now, I have to speed this footage up because we clocked in at a fairly lengthy 24 minutes and 10 seconds. Honestly, seeing this really puts into perspective how hard it would have been just to test new code in the game. Sure, most of the time you'd only be recompiling the bit you worked on, not the whole thing, but if you were working on something big enough that each time you wanted to test it, it had to recompile even just 20% of the code base, that's a pretty significant chunk of time you'd have to be sitting around for. Now let's do the exact same thing on a modern PC. This is my main system. It's an i9-13900K, and we're running it through Wine because this is a Linux household. On here, the compile comes out to just 43 seconds, a pretty huge improvement, well under a minute. But wait, this is an old compiler. nearly 30 years old in fact. It's lacking decades of technological innovation, optimizations, and most importantly, only allows single-threaded builds. What would happen if we used a modern compiler like GCC and compiled across all 32 threads of this CPU? Just over 7.5 seconds using a modern compiler on modern hardware. That's just mind-blowing to me. The entirety of LEGO Island, the entire year-and-a-half-long decompilation, all of that code behind all of those childhood memories, all of it comes together today in only 7.5 seconds. Part of me thinks decompiling games is worth it just for this, just to see exactly what went into these games, just to see how far we've come. After releasing the LEGO Island documentary, which itself was shortly after the decompilation completed, a LEGO employee reached out to me asking if I could help them find more LEGO Island development material for their internal archives. I sent them some stuff I'd obtained over the years and pointed them in the direction of where they might be able to find more. Well, wouldn't you know it, a little later on I was told that they had actually managed to find what seems to be a copy of the final retail source code. And no, we can't have it. It's incredibly ironic that part of the reason I started the decomp all those years ago was because we had all assumed the source code was lost forever, and only after the decomp is finished does someone actually find a copy. Does this mean we're going to see an official remaster or re-release anytime soon? Well, it's impossible to say. This was merely a single employee's effort to improve LEGO's internal archives, not a company-wide push to do anything with it. Things like this don't happen overnight. They would have to weigh up how well it would sell versus how much it would cost to get it into better shape, negotiate any necessary licenses involved, all before any actual work would begin. But hey, if they ever do decide to do that and need some help, I know some people who are already familiar with the code and what would need to be done to make it more compatible with modern PCs. So we made it. LEGO Island has been decompiled and we can do whatever we want with this code now. There's still a lot to do as far as making it easier to use and more portable, and if you want to help out with that, I'm sure the team would love to hear from you. Already I can see people starting to attempt ambitious things with it, and honestly, that's what makes me most excited about decomps in the first place. I can't wait to see what people end up doing with this in the future. This will probably be the last LEGO Island video I make for a while. I mean, if there's a big milestone, I'll probably cover it either here or on my second channel, but otherwise there are a lot of things that I'd like to start working on and making videos about that I've kind of been putting off until now. If you're interested in more LEGO Island content, I did release a feature-length documentary a few months ago where I interviewed nearly all of the people who worked on it and visited key locations like the old Mindscape offices where the game was made. And on my second channel, we just covered the resurgence of LEGO Island speedrunning, featuring discoveries you can only make by playing the game over and over, not just staring at the code like we do. But after all that, I think I'm due for a break from thinking about this game for children. Finally, I'd like to give a bit of an update on the channel. I'm sure some of you are wondering why I've only released like 4 videos in the last 2 years. I hadn't wanted that to be the case, it just kind of worked out that way. Last year especially, the videos I put out were just really big, like the .NET 95 video took 4 months to make, the LEGO Island documentary took like 6. But I've really missed having more of a back and forth with you guys. Like, I love working on these bigger projects, I love working on these bigger videos, but I don't love disappearing, you know? I wanna try getting back to putting out stuff semi-regularly again. The idea was I would post really quick updates on Patreon and then release bigger videos once projects were done, but everything has just taken longer than I expected, so I want to look at trying a different approach. I'm still figuring out exactly how it's going to work because the reality is my projects have just grown a lot in scope. You know, I'm no longer just replacing a couple capacitors on a board and making a whole video about it. I'm doing decomps and reverse engineering and writing apps from scratch and occasionally making a full-blown documentary, and all that stuff takes months, if not years, not a couple of days like it used to. So it may take some time to find the right balance between doing all these bigger projects and still putting out semi-regular videos that I'm proud of, but ultimately I think talking about this stuff is better than not, so it's something I want to try. Anyways, with that being said, I hope you all enjoyed this video, and I'll see you all hopefully pretty soon. Bye guys. Just before you go, I want to give a big shout out to my patrons and YouTube members who help this channel operate without sponsors and allow me to spend time working on bigger projects and videos just like this one. If you'd like to support and see both bonus content and main channel videos early, consider signing up at patreon.com/MattKC or youtube.com/MattKC/join. Links in the description.